All right, we are in Unit 2. Again, we are summarizing chapters 7 through 10 roughly all in one video, which I'll sprinkle in later videos all around that. But the point is, we were talking about and still continuing to talk about scatter plots and least regression lines, things like that. And my point is, again, as you're taking these notes, if I'm moving too fast, you need to slow down. You pause the video. That's all you got to do. I'm going to keep going at my pace. You remember to pause and then write down what you need to and rewind if you have to as we go. So correlation and linearity is where we left off. And although a scatter diagram usually gives an intuitive visual indicating when a linear relationship is strong, in most cases it is quite difficult to visually judge the specific strength, right? You can't just sit there and say, yeah, it looks strong and move on. We got to have a definitive mathematical way of saying that. For this reason, there is a mathematical measure called the correlation or the correlation coefficient. Okay, so there is a mathematical thing with this. So, important as correlation is, we always need to keep in mind that significant correlation does not necessarily indicate causation. All right, what I mean by that is, we can see that maybe it is appearing to look like a straight line, but is that necessarily enough just by looking at it, is what we're getting at. Correlation measures the strength only of a linear relationship, right? Correlation measures the strength only of the linear relationship. So here's the formula. Now, feel free to write the formula down, but here's the good news. I don't think I've ever seen a problem where they expect you to take this formula and figure it all out. But this is, again, the number of items that are in the problem. This is basically what they're doing is, if you notice, it kind of looks like all practically a z-score of one variable and a z-score of the other is kind of what it roughly looks like. And you're adding them all up. It looks like what you're doing. If you remember, that kind of looks like the z-score formula, and that kind of looks like the z-score formula, and it kind of looks like, again, you're adding them all up with the summation. So you multiply them and you add them all up, and then we're dividing by, which, if you remember, when we were finding, was it the standard deviations and the means before, we were actually not using n, we were using n minus 1 for an overestimate. So the point is, we can get this in the calculator and we'll probably never have to use that formula by hand, but there it is, so feel free to write it down. Important again, correlation does not imply causation. Correlation does not imply causation. I will explain that a little more clearly later, but this is how it's worded on the exam, and they will try to trick you with it. So I'm writing it this way repeatedly over and over again and making it bold so you can see it this way. Okay? So take a look at the formula again so we know where it's coming from. So the formula is technically the sum, right? The sum of the products, that's that times that, of the z-scores, all right, divided by 1 less than the sample size, and normally means the sample size is where it's coming from. And again, your calculator will find the correlation quickly for you, but when I show you the formula in detail like this, it helps you to understand where correlation is coming from in case in the future you have to manipulate anything to be helpful for you. So also notice that changing units does not change the correlation, since the correlation formula is based off a z-score, and that's very important. Remember, I could be working with 2 different units comparing 2 different ideas of items together, but if I convert them both to z-scores, it's not going to matter, because z-scores are everything in terms of the same standard deviations, the same basics, the same units. You're putting them all in the same idea, so you're standardizing them is what you're doing. So also notice that changing units does not change the correlation, since the correlation formula is based off of the z-score, right? So it's not going to matter. So note from the formula that correlation does not distinguish between which variables are called x and y. So that's not going to really make a difference either, because you're multiplying them at the end of the day, so it doesn't really matter. And since means and standard deviations can be strongly influenced by outliers, because they can, right? Means, standard deviations, and that's what we're basically focusing in on here. They can be strongly influenced by outliers. Correlation is also strongly affected by extreme values. So you have to keep that in mind, right? Outliers, all right? Data that, like that one where we have the line going down like this, when you have the 1 point randomly down here, it can be strongly affected by outliers, which means the mean is also affected in the standard deviation, and that's technically what's happening in here, mean and standard deviation. Just got to keep that in line. It will affect our correlation. So here's a tip. With standardized data like z-scores, R is the slope of the regression line. Okay, so once you standardize those things with standardized data like z-scores, R is the slope of that regression line that you're going to find. Okay, the value of R always falls between -1 and +1, with -1 indicating a perfect correlation, but a negative correlation, and +1 being a perfect correlation, but positive, right? And correlation of 0 does not mean there is no correlation. That is not what that means. All right, correlation of 0 means it's the slope of the line. If that's what we're talking about, so the slope is a straight line. It just means there has no linear relationship between there. There's nothing linear about it. That's all that it means. Okay? It just means there may be a non-linear relationship. All right, is the key. A non-linear relationship. So, +1, all right, because it's pretty close to a straight line going up. All right, but this is exactly 1 because they're on a line. There's a difference. Pretty close, exactly 1. This is pretty close to -1. That is also pretty close to -1, right? Just things to look at. All right, but this is close to 0. It's kind of all over the place, right? I can't tell you if it's positive. I can't tell you if it's negative. It appears to be kind of all over the place. So I can't find it's looking like it's nonlinear is the point. All right. It can be shown that R squared, if you take that slope that we're talking about, whether it's positive or negative, and square it, is also called the coefficient of determination. R squared is the ratio of the variance of the predicted values to the variance of the observed values. That is, there is a partition of variances, and R squared is the proportion of this variance that is predictable from the knowledge of the input value. All right, lots of words there. And we're getting to some more examples as we go through here. I'm just trying to give you the piece together the background of all of this. Basically, we can say that R squared gives the percentage of the variation in the Y or output that is explained by the variation in X or the input. Okay, so what is explained? It's giving me a percent. Okay, the R squared is giving me a percent. Remember, R can be positive or negative, but when we square it, it's always going to be positive, so it's that percent we're talking about. So while the correlation R is given as a decimal between -1 and 1, the coefficient of determination is usually given as a percentage. R squared of 100% is a perfect fit. That's telling you that the line you have is a perfect fit. Scientific experiments normally aim for your R squared in the 90% or above range. If so, it's looking pretty good. All right, I'm seeing a relationship between the two if I can reach that 90% or higher. All right, observational studies with R squared at 10% to 20% might be considered informative. I know there's a big chunk in between. If we're saying anything 20% and below, yeah, throw it out. I'm not really seeing any data. Anything 90% and above is like, oh yeah, that's good, that's good. But what happens in that middle? Exactly. What happens? That's a big, big middle. All right. So note that while a correlation of 0.6 is twice a correlation of 0.3, and it is, the corresponding R squared of 36 is 4 times that, which is 9%. So let's take a look at an example. All right. The correlation between total points scored and total yards gained for the 2016 season among a set of college teams is this, right? So the correlation between total points that they scored and total yards that they gained was this. What information is given by the correlation of determination? Well, that's basically R squared. If I square it, that's close to 71%-ish, right? Thus, around 71% of the variation in total points scored, right, and total points scored can be explained by a linear relationship between total yards gained. Basically what you're saying is 70% of the data can be explained by a linear relationship of total points scored. 70%-ish of the data. Okay? Not all of it, but 70% of the data can be explained between total points scored and total yards gained. The other 29.44-ish% of the variation in total points is unexplained. All right? So that's where we might end up getting some outliers, something that's a little hazy, something that's a little fuzzy in the data. Maybe a certain team won, but they didn't score a lot of points and they didn't score a lot of yards because there could have been fluke plays that happened. So maybe that happens. Note, alternatively, you can say that 70.56% of the variation in total points scored is accounted for by the variation of total yards gained. And note, we can also say that R squared gives the percentage of variation in Y that can be explained by the regression line as the explanatory variable. So basically, the X can be explained by whatever percent of Y, right, is basically what you're finding. So when we come back, we will look at the least squares regression line.